like that. They give you all the details. Chapter 3 lets us move on to numerical measures. Okay. We've talked about populations. We've talked about samples. If you have a sample, you have a thing called a statistic. If you have a population, you have what's called a parameter. This is really the only time we make a big distinction between these things, but I also find it very interesting. So I used to be a really huge baseball fan. You have the back of the baseball card and it has all their stats on it. But by definition, if I know everything about the player, I'm not taking a sample of their data, I have the whole population of their data. Technically not baseball stats, also technically baseball parameters. Just doesn't have that same feel though, does it? No. So we call them baseball stats. That's the difference. Once we have this sample statistic, and that's mostly what we will use, right? We rarely ever have our population. So we use a lot of statistics. Why is the field is called statistics? If we just have one value, we're going to call it a point estimator. Okay. So basically that's what a statistic is. It's an estimate about our sample that we're going to estimate our population with. Okay? Because, let's say, room. I try to figure out the average age of this side of the room. Then I try to figure out the average age of this side of the room. What is the likelihood that the two average ages in this class are going to be the same? Look around. See if you still want to make that assumption. Not that I'm picking on anybody. Here, wait. Let's make this easier.
Are we removing outliers or no?
No. Okay. Now I'm on this side of the room. I'm pretty sure I'm older than most of you in here. Okay. So now you have to add me in. So now if I take the average age of this side, and then I take the average age of that side, right? So one population, two different samples. What's the likelihood that I'm actually going to get the exact same, down to the third decimal point, average age?
Not likely.
Not likely. Okay. It may be really close, okay, but it's not that I'm going to get the exact. So that's the idea. We're just estimating, right? So if I took the class, and I assumed that this was a good representative sample of the class, then I could feel confident, assuming that that's the average age for the whole class. But I could also, if this is a good representative on this side, I could make that same argument. Okay. So we're going to talk about point estimators this week. In 2 weeks, we'll talk about, is one number enough, or should we add an interval around that one number? And then maybe we can be even more confident. See how confidence levels get it for these things. But that's how they connect, okay? So we have three big things. When we're talking about measures, when we're using numbers, or we're talking about numerical measures. We've got measures of location, we've got measures of variability, and we have measures of shape. So let's start with measures of location. Mean, median, mode, weighted mean. Everybody good with the weighted mean? You're like, yes, I have a GPA, I understand weighted means. Okay. A geometric mean is a little bit different. You're actually taking an nth root. Finance majors. Geometric mean is more popular in finance things than in other fields. We're not going to focus on it. I just want you to know that it exists. Percentiles, quartiles, all of these are measures of location. Okay. So I have a data set up here. It's tiny. 70 apartments. I have the rent for 70 apartments. Okay. Looks a little crazy at the moment, so I decided to order it from smallest to largest. I can find the average, the mean. For some reason, mean didn't come. We'll get into all the technical symbols and stuff later. Right? We have the average. We have the median. We've got the mode. 3 different measures of location. If I'm trying to sell apartments, which value might I say is the average for apartments around campus? Let's try it. Which value would I want to use? Which value would I want to market? I got mean, I got median, I got mode. Somebody tell me why I would want to do the mode.
It's not just number of friends.
It's not accurate, but
It's not accurate, but it's the lowest. Marketing matrix? No, I'm just kidding. Just kidding. It's the lowest. So if I want to be like, hey, low apartments, come over here, maybe I want to use this. Somebody tell me why the average? Why the mean?
I like the more true
More true? More true to what?
of the sense of the sample size. Like if I was going to look for an apartment and you gave me the mean, I'd be like, okay, I expect to pay $600.
Okay. So that's going to include the low prices, it's going to have the high prices in there, it's going to be, okay. Somebody who said median, why the median?
Not as susceptible to outliers.
Okay, less susceptible to outliers. So if I have that one really high-priced apartment, it's not going to take that into account. Or that one really low apartment that you know you really don't want to live in, not going to take that into account. Okay, so it's going to be more what's hidden in the middle. Would it be wrong or unethical to report any of these numbers? Food for thought. So the other measure of location that we have is percentiles or quartiles. Anybody that's taken a standardized test always has to find out what percentile they were in on that test, right? The way we actually locate the percentile is with this formula. The way that we're actually going to do it in this class is we're going to ask SAS, what is the 75th percentile? We're ask Tableau, what is the 90th percentile? And it's going to be like, here you go. Okay. But to actually do it, you figure out what percentile you want, you divide it by 100 to make it work. You take your sample size plus 1, you multiply those two things together, and that's going to give you the location. So we're going to have to go find the, in this case, 53rd value. Once we find it, then we're going to find the 54th. We're going to take a look, because it isn't just the 53rd. You got to take a little bit extra to find the exact percentile. It's a little complicated. It's not hard. Just not a lot of fun. And that's assuming that you have all of your data listed in an ascending order. Okay. Measures of location. Measures of variability. Again, if you guys have questions, stop me. I'm hoping most of this is stuff you already know. Just a refresher. Measures of variability, right? So we can find the location of some data point, right? The middle-ish data point, right? We do the median, the average data point, the most popular data point. The measures of variability, we have the range. Once we have quartiles, we can do this thing called the interquartile range, the range in the middle 50%. We can do variance, standard deviations. We can do this thing called a coefficient of variation. That's the one that people haven't heard of quite as often. Okay. So using our same data set, the range, the big minus the small. The quartiles, we can use our percentage to find the 25th is the first quartile, the 75th is the third quartile. Once we have those, we can find the interquartile range, or the range of the middle 50% of your data. We can calculate the variance. We can calculate the standard deviation. And again, we're just looking at measures of variability. Is my data really spread out, or is it really packed up together? Okay. So when we're talking about variance and standard deviations, everybody's good with the standard deviation is the square root of the variance. Do you know why we take the square root?
It's supposed to.
Okay, we want it to be positive. big reasons, right? So as we're creating the variance, we're taking a data point, seeing how far it is away from the mean. We're adding up all those differences. And when we add up all those, we're going to have just as many data points above the mean as we have below the mean. They're going to cancel each other out. So we have to square it to get rid of all the negatives. We want it all to be positive. But when we square it, let's say that I'm interested in figuring out, looking around, the average number of cups of coffee that you guys drink to stay awake in my class. Okay. So we have the average, and I want to see how variable that data is. And as I'm doing that, squaring everything, and now I end up with cups of coffee squared. Not square cups of coffee, just cups of coffee squared. Okay. Can I talk about cups of coffee squared? That doesn't make sense to us, right? So instead, I take the square root of that, and now I'm just talking about cups of coffee. That's really the whole reason. You take the square root of the variance to get the standard deviation is to get it back into the right units so that they're in the same, the mean and the standard deviation are in the same units. So, it wouldn't make sense to talk about a variance of $30,000 squared. Dollars squared? We don't have dollars squared. We have dollars. So if I take the square root, now I can say the variability is about $55. So I'm going to tell you that here's my average of $590 with a variability of about $55, depending on if you go to the higher end or the not as awesome apartments. The coefficient of variation just takes that standard deviation, divides it by the mean, and turns it into a percent. So we're going to say that the variation is about 9%. Okay, cool. All right. More fun things. We can measure the shape. Seems kind of weird. We can measure the shape. We can measure a relative location, so not the absolute location, but a relative location. And then, you guys have already mentioned, everybody loves to know, what do you do with the outliers? Okay. So, when we talk about the distribution, we've already talked about skewness. There's actually a number that goes with skewness. You can actually calculate how to do something. There's a z-score. This is how we're going to standardize our data. We have a theorem and a rule. We have Chebyshev's theorem. We have the empirical rule, what you said quite a bit. And then talking about detecting outliers. So again, our same data, I have a histogram of our data. Would you say this is normal, skewed left, skewed right? Skewed right. Skewed right. And would you say it was highly skewed, moderately skewed, mildly skewed? My vote's for highly skewed. Okay. So I actually have a number, 0.92. Is that a positive number or a negative number? Positive. So if it's a positive number, then I'm going to be skewed right. So what do you think a negative number would tell me? Alright, so negative value is skewed left. Okay.
Is there a limit?
There is not a limit. So 0 is kind of your middle ground, right? So for a normal distribution, it's not skewed at all. Skewness is 0. The farther you get away from 0, the larger the skew. Okay? So if I was to extend this and add on one little outlier way out there, now my skewness probably goes from a 0.92, maybe I'm just totally making this up, 0.268. So there is no upper limit because of how it's actually calculated. But generally hitting 2, 3 is about as skewed.
So your 0 is your normal distribution.
My 0 is my normal distribution. Yeah. So skewness of 0 is my normal distribution. We'll talk more about that next week.
So would a point of 92 normally be considered highly skewed then?
I would say when you start to approach 1, I would call it pretty highly skewed. And these adjectives are very subjective. You know, so it's like you're looking at this picture and we're like, it's highly skewed. There's no cutoff to, if the skewness value is above 0.8, then it is highly. So.
What's the population for that?
That is an excellent question that I'll share with you after class because I don't know it off the top of my head.
Okay.
It is the third moment. So a mean is the first moment, the variance is the second, skewness is the third, and a thing called kurtosis, which is really how tall or how flat our distribution is the fourth moment. And so that's like pure stat stuff. So if you're interested, we'll look it up. The next thing we have is, have you ever been told that you can't compare apples and oranges? Well, if you transform them into a z-score, you can compare anything you want. Okay. Normally we don't compare apples and oranges. But, how do you take the ACT test? How do you take the SAT? Okay? The ACT and the SAT are two, you take them in high school to try to get into college. It's like the GRE for high school students, right? But some people, depending on what state you're in, take the ACT, some people take the SAT, and as an admissions person, I've got to figure out ACT or SAT. I have this issue when we have GRE versus GMAT. How do I compare a student who took 2 different tests? And the answer is to standardize it. Okay? So you can take 2 data points that are on opposite or on different metrics, convert them into standard scores, and then you're able to compare them. So for example, the formula here, and we'll use this semester, we'll use this next semester, this is one of those things you want to learn. What we have here is we have a raw data point. Okay? So this right here, ooh, that was almost as bad as our words. I apologize. Right, so we have a raw data point. I'm going to subtract it from the mean, so I'm going to see how far are you from the mean, and then I'm going to divide you by the standard deviation. Okay, so I'm going to take a data point, that data point right there. I'm going to transform it into standard deviation, units. So now instead of talking about points on an ACT score, points on an SAT score, or if I'm converting people who have run a 40-yard dash versus a 40-meter dash, right? Yards versus meters, you can't directly compare, right? So as long as I'm just converting units, I'm putting them on a standard scale, and now I can compare them. Okay. And so this is what happened to all of those data points. So you can pick out a data point, try this, and see what happens. Okay. So our mean value was 590, right? So red, here's our mean value, 590. So if we go and find the corresponding 590, there were some decimal points. It was 590 point something. So a z-score of 0 is the mean. Okay. So if I go over to my next slide, here's a picture of my empirical rule. And what this shows us is this is a z-score of 0. And then if you go one standard deviation away from the mean on either side, about 68% of your data falls in that space. You guys all familiar with the empirical rule?
Yeah.
Yes. 68, so 95, 99.7. Everybody's good? Yes. I did this on Saturday. Everybody was not good. Culinary games. They were great. They were wonderful. They just didn't remember this part. That's okay. All right, so we've got the empirical rule. The empirical rule, the only bad part about the empirical rule is it has to be a normal distribution. So this is where that whole Chebyshev's theorem comes in. What it does is it actually uses the z-score and does a tiny calculation to tell you what percent of the data falls within a certain z-score. Okay. And it doesn't have to be a normal distribution. We're not going to use this, we're not going to do it. It's just stuff that in a stat class you need to at least heard of Chebyshev's theorem. Alright, let's see what I have left. 5-number summary in the box plot. Everybody go with this? We love 5-number summary. What are our 5 numbers in our 5-number summary?
Min, first
Minimum?
quartile, median, third quartile, maximum.
Excellent. So the minimum, first quartile, median, the third quartile, and the maximum. You take the middle 50%, the first quartile, the median, and the third quartile, and you make your box. You add on your lowest value and your highest value, and you put on your whiskers. And then if I wanted to detect outliers, there's a formula. You start at your 25th percentile, and you subtract 1.5 times your inner quartile range. And if you get a value that is farther than that, it's going to be considered an outlier. You do the same thing on the upper limit, and you can determine outliers in that way. SAS is going to do this for you, and it'll just represent it with a little asterisk if there's an outlier. And this is the formula that they're going to use. In terms of back here, if you get above or below 3 standard deviations away from the mean, these are outliers. Now I'll talk about what we're going to do with them later. The first thing we want to do is just figure out ways to identify them. Okay? So if you're talking about the means and standard deviations, you're going 3 standard deviations away from the mean. That's going to be an outlier. If you're looking at medians and interquartile ranges, then if you get above this upper limit, and in this case the upper limit's like right here at like 745 and down here at 425, so you can make it past those marks. This is 745, this is 425. You get out here, that's where the outliers are. Okay, so a couple different ways to detect them.
So the 745, is it considered as outlier?
So
If the
yeah,
data point is on 745.
I think you can make your best call. So if there's a bunch of data right around, data points right around 745, then not an outlier. But if it, the last value we had was 715, then 745, I'd say it was an outlier. Questions, comments, thoughts? If we've got 2 variables, correlations. There's math to that, or there's a button we can push. Everybody's done a correlation, right? Correlations. Yeah. Did you ever have to do the correlation by hand? You're like, here's the x, this chart right here, here's the x, here's the y, subtract them, multiply them. Yeah. This is an analytics course. We have software, but the idea is knowing what a correlation is. The relationship between our 2 variables. So would you say that this is a strong correlation? 0.96. Yeah. It doesn't get much better than that. Okay. And then we said positive or negative. Negative. So if we were to draw a picture of this real quick, assuming that's straight, it probably looks something pretty close to that. Brilliant. We've already talked about dashboards. Which one should I pick? So one of the things that my students in the past have liked and wished that I would have incorporated sooner, is I'm going to try and give you guys a concept map to kind of go throughout the course and see how this all stuff ties together. Right now we've talked about continuous variables, we've talked about categorical variables, and we can visualize and describe any of them. Okay? As we go throughout the semester, we'll have certain tasks that'll work, or certain methods that will work with some of these variables and not with others. And we'll kind of keep track of all of that. But for right now, with visualization, description, we can do that with any type of variable.